Day 29, page 712, problem 52. Let's apply Kirchhoff's laws to this. Once again, I'm not going to get involved in drawing a lot of diagrams, so listen carefully. In that middle branch there, you have 3 amps. We can't really use Kirchhoff's first law right now because we're only given one of the currents. So I'm going to go to law number 2, that is the sum of the voltages in any given loop adds up to 0. The total potential difference is 0 volts. But in this middle branch here, using V equals IR, 2 times 3, I have 6 volts here. So that's 6 volts. Then I look on that left-hand loop. In this loop right here, I have 3 elements. And if we assume that the current is going that same way, I'm going to use blue to indicate it's most likely true that the current is going this way in this resistor in that branch. That's a 6 ohm resistor there. But if we look at that then, assuming the current's going to the right, that resistor must have 6 volts, because I can see in that loop we have a positive 12 volts for the battery, and the other resistor is technically a negative 6 volts. So this resistor right here must be 6 volts. We do red on that. And if that resistor is 6 volts and its resistance is 6 ohms, then its current must be 1 amp, applying V equals IR. So that blue arrow there is 1 amp. I'm going to go with blue. 1 amp right there. Well, if that's 1 amp going into this junction right here, and there's 3 amps coming out in that middle branch, that means over here on this side there must be 2 amps. Because if you have 3 amps coming out of a branch, or out of a junction, this junction right here going straight down, there must be 3 amps going in. So 1 plus 2 is 3. So if there's 2 amps in that top resistor up there, then that must be 2 volts, because V equals IR. 2 volts. And therefore in that right-hand loop, if I follow the right-hand loop around, let me use red. So if I go down, over, up as my loop rule, those 3 elements must add up to 0 volts, 0 potential difference, and the resistor is going to be negative 8 volts, so the battery must be positive 8 volts. And I think that's the final answer. We're looking for the unknown voltage source and the power delivered by the 12-volt battery. Well, that's pretty easy. For a battery, you have to use P equals VI. Can't use I squared R because we don't have a resistance in an ideal. Well, even if it is an ideal battery or not, you still calculate the overall power delivered by P equals VI, not P equals I squared R. So it's just simply 12 times, 1 amp. Power is 12 watts. The other battery is supplying 16 watts. 8 times 2 is 16. And then you can figure out how much energy was used up by all the different batteries, or different resistors, I should say, in the circuit. That should add up to 28 watts. If you're supplying 28 watts, it's being used up by the resistors 28 watts. If you want to go and explore that, you may. Well, just out of curiosity, if you do it real fast, if you do a P equals I squared R on each resistor, this 1 ohm resistor, I squared is, 2 squared is 4 times R. The upper right-hand resistor, the power is going to be 4 watts for this resistor right over here. The 6 ohm resistor, it's I squared R. 1 squared is 1 times 6 is 6 watts for that resistor. And the one in the center here, I squared, 3 squared is 9 times 2 is 18 watts. And if you take those 3 wattages, powers, add them up, you get 28 watts being used up or turned into heat or light, and supplied 28 watts by the 2 batteries. It is also interesting that the smaller battery is providing more power, mainly because of the current over there with the smaller resistor.